Let's make another example using the modified separation of variables where the PDE is a non-homogeneous PDE with non-homogeneous boundary conditions. Okay. Example 3. Non-homogeneous PDE with non-homogeneous boundary conditions. And let's use this heat equation, the heat of the rod, which is 1D from 0 to L. And we have our U0T, the boundary condition is equals to a fixed temperature. ULT is equals to a fixed temperature. So this is fixed temperature boundary conditions. And let's have an initial conditions, which is ux0 at t equals to 0, time equals to 0 is equals to fx. This fx is can be any continuous function or some constant numbers. Then using this fx, basically later we are trying to solve the coefficient for the Fourier series. Okay, so this is the initial conditions. And we have how we can have the non-homogeneous PDE. First, you will think about how we can have the homogeneous PDE before. So the homogeneous PDE is ut equals to alpha uxx. When I have constant thermoconductivity, constant density, constant heat capacity, then we can, and also no heat source, then we can have this 1D heat equation with homogeneous PDE. Then how we have the non-homogeneous part? We can just simply add a Q term, which is the heat source as function of x only. So this is a constant heat source as function of time. It's not changing by time. It's a simplified problem. So when you have this heat term, this PDE is not homogeneous anymore. Then how we can solve? We can use, again, the separation of variables, the modified version, modification. And how we can have that simply or similarly as what we have before, the uxt can be equals to vxt plus wx, where this uxt is a homogeneous PDE with homogeneous boundary conditions. And this wx is simply a steady state heat distribution. Okay, and with this part, the separation part, uxt equals to vxt plus wx, then our ut become vt, because only the v function part is as function of time. So ut equals to vt equals to alpha uxx plus t. So this become our new partial differential equations. And with the above assumptions, what we can get? What assumption? First, the VXT is a homogeneous PDE with homogeneous boundary conditions. Then what we have? We have VT will be equals to alpha VXX, homogeneous PDE. V0T will be equals to VLT equals to 0 because that is a homogeneous boundary conditions. Then how about our omega part? That is a steady state temperature distribution. So the UXX, okay, from here, will be equals to VXX plus W double prime. Okay, so that is the from this part. And we have our W 0 equals to UL, WL equals to UR because they are the steady state temperature distribution. it won't change for the end of the route. It's always fixed temperature. So WL equals to UL, W0 equals to UL, WL equals to UR. It's always true. Then at the steady state, we know that the temperature is not as function of time anymore. So UT equals to VT equals to 0 at steady state. Temperature is not depending on time. So UT equals to VT equals to 0. And what is UT? It's alpha UXX, alpha UXX plus Q, right? What is UXX? It's VXX plus W double prime. So it's alpha VXX plus alpha W double prime plus Q. And this equation will become 0. And since VT, okay, VT equals to alpha VXX, so since VT equals to alpha VXX at the steady state will be equals to 0, then we only left is alpha W double prime plus Q equals to 0. So W double prime will be minus Q over alpha. Okay. Then we can directly get our W. What is our W in the end? So the W, since W is equals to W double prime equals to minus Q over alpha, then our W is basically a second order of temperature, second order as function of x with the slope is minus Q over alpha x squared. Then the first order part will be Cx plus D. Then you can use W0 equals to 0, WL equals to 0, trying to figure out what is the C part, the constant part, what is the D part. So when x equals to 0, the W0 equals to UL, the UR, it's just a fixed temperature. It can be 0. It can be 0, but it's in general, it's a fixed temperature there. So when x equals to 0, W equals to D equals to UL. When x equals to L, then you can figure out the W is equals to minus Q over alpha L squared plus CL plus D, which is UL, that is UR. So you can get what is the C, what is the constant C. Then after that, you can also, that is basically the W term, which is the steady state part you already figure out. How about in the transit? The add transit, which is the V part, transit. So Vt equals alpha Vxx with V0t equals to VLT equals to 0. This is a homogeneous PDE with homogeneous boundary conditions. And you can use directly the separation of variables to solve this part. So V xt can be separate to fx and gt, and you will use SOV to solve it. In the end, we already solved this part. The Vn equals to the sum Cn sine n pi x over L e to the minus alpha n squared pi squared over L squared t. And you have Vx0, which is the initial boundary conditions. Vx0 equals to ux0 minus wx. And the ux0 is ufx. The wx is whatever you solve here. Then you can try to use Vx0 to figure out what is your Cn part. Then the Cn will be equals to inner product of Vx0 sine m pi x over L normalized by the normalization factor, the inner product of sine m pi x with itself. Okay, then finally, you know the Cn, you know the Vn, you know the W, you know what is Ux t. Finally, Uxt will be the sum of Cn sine n pi x over L e to the minus alpha n squared pi squared over L squared t plus minus q over, this is 2 alpha x squared plus cx plus d. So that is your final solution of the PDE, non-homogeneous PDE with non-homogeneous boundary conditions.